A54C, obviously atmospheric rivers, same title, but I encourage everybody to attend that. It's going to be a brief but good session at 1:45 p.m. And then this afternoon, normal time, a in-person poster session that again I encourage everybody to attend. Both will have some very nice presentations. Okay, so with that, let's get started. We'll welcome our first speaker, Kirsten Hall, who's going to tell us about ozone anomalies associated with atmospheric rivers. I think you should be good to go.
Okay.
You have 9 minutes total, and this is your setup. Is that okay? Yeah. Feel free to.
All right, good morning, everyone. Thank you so much for being here. My name is Kirsten Hall. I'm a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics, and I am going to kick off this atmospheric river session talking to you primarily about ozone. Specifically, I'm talking about the increases in tropospheric ozone due to stratosphere-troposphere transport. These stratospheric dry intrusions change the concentration of ozone in the troposphere, which affects radiative forcing, as ozone in the troposphere is a greenhouse gas, especially in the upper troposphere. This can also increase ozone at the or near the planetary boundary layer, which of course ozone there is a pollutant harmful to humans and entire ecosystems. Stratospheric ozone frequently enters the troposphere through eddy exchange events associated with global circulation wave patterns. However, these deep dry intrusions of STT they tend to be very sporadic, which makes the regional ozone flux variable and difficult to characterize, and therefore an ongoing active area of research. There's a large body of work, fairly large at least, existing studies on the STT ozone flux associated with the cold, dry intrusions of extratropical cyclones. This paper I'm referencing here is a global climatology of this phenomenon. I'm going to talk to you about this, of course, in connection to atmospheric rivers. So atmospheric rivers, there's not one clear definition, but they are approximately 2,000 kilometer long rivers of water vapor transport. They are most frequent during each hemisphere's respective winter. They're responsible for vital precipitation upon landfall when they're of low category or lower intensity or less duration, but they can also cause catastrophic damage and very important to understand. They occur in conjunction with extratropical cyclones about 80% of the time, but they're very distinct in their intensity, their location, and their duration. So what I'm talking about here is a distinct measurement phenomenon. I'm primarily using data from the reanalysis data set from MERA-2. This assimilates meteorological and ozone observations to produce meteorological and chemical products at very high spatial and temporal resolution. But I also compare this to ozone profiles from the ozone monitoring instrument, which is a little bit coarser resolution and can't detect ozone quite as deep into the troposphere. This figure I'm showing here is as a comparison of the two, but I'll kind of explain in a little bit more detail. You'll see a few more of these plots in a few slides. So I'm implementing an atmospheric tracking algorithm over the Northeast Pacific and Western United States to start with. I'm identifying the atmospheric rivers using existing binary catalog files that are provided by ArtMip, which is really fantastic for me. In particular, I like the Rutz et al. 2014 catalog, but others as well. And I'm computing the integrated vapor transport over this field, and I'm following the peak value of IVT throughout the lifetime of each atmospheric river event. So in this little GIF, I'm showing the red X marks the spot of the peak value in IVT, tracking an atmospheric river until it dissipates and then moving on to the next one. And this is so that I can get a wide range of atmospheric river intensities, and that'll become apparent in just a moment. So here we are on the left-hand side. This is tracking a particularly intense atmospheric river event that made landfall on the US West Coast in December of 2010, causing catastrophic flooding and mudslides. On the left-hand side, I'm tracking, you can see, this is my algorithm, tracking the atmospheric river event as traced by the IVT red contours. Also the black arrows give you an idea of the intensity. You can see it's finishing off an event at December 10th and then picking up the development of this intense event. You can also see in the shading the ozone anomaly. So the green is the positive ozone anomaly. You can see this filamentary structure that is sort of tracing the long axis of the atmospheric river event. On the right-hand side, I'm showing the vertical cross-section that's denoted by the black line, following across approximately the peak in IVT, as well as covering this ozone anomaly. And what you can see through on the right-hand side, again, shading is ozone anomaly. So this is the anomaly at that particular time minus the 10-year climatology of ozone in this region. So you can see on the right-hand side, the red contours are now the vapor transport, not the integrated value, but you can see the vertical structure of the atmospheric river in red. The black contours now are potential vorticity contours, so the PV values, with the white contour tracing the PV equals 2, which is a measure for the dynamical tropopause. And you can very clearly see this dry intrusion event following behind sort of the front of the atmospheric river, behind the cold front. And so this is exactly what I want to investigate further in a sort of more statistical sense. So I ran this algorithm tracking all atmospheric river events in the Northeast Pacific between December 2004 and 2014 and generated these composites. So what you're looking at now are latitude by longitude composites at 400 HPA. So this is now into the troposphere, the ozone anomaly there, centered on the peak value of IVT for each time step of the atmospheric river event. I've binned these according to atmospheric river direction of travel. As you can tell by the black contours. And this is because the excess ozone that we detect is dependent on the atmospheric river direction of travel, right? So if I'm averaging rivers going east with those going north, I'd be washing out that anomalous phenomenon. Of course, I could rotate the field of reference and just create one large composite, but I'm actually curious about whether or not there's any dependence on atmospheric river direction of travel. So I've done it this way. I also was curious about any dependence on the atmospheric river intensity. So I divided into 2 bins, just basically 50th percentiles of all atmospheric river events between December 2004 and 2014. So I get 2 bins of peak intensity as well. And I'm kind of just looking for any trends or dependencies in the total ozone concentration. So now on the left-hand side, I'm showing the composite maximum value for ozone anomalies at 400 HPA in the troposphere. On the x-axis, this is just each of those bins' direction of travel. The scatter about this on the left-hand side, I don't actually think is that meaningful, but what's important to notice is that the orange points are for high-intensity atmospheric river events and the blue points for low-intensity atmospheric river events. So we see a clear distinction in the total amount of ozone concentration at 400 HPA in parts per billion by volume. And this is the anomalous ozone contribution. On the right-hand side, I investigate this as a function of the dry intrusion depth, right? So how deep on average into the troposphere is the dry intrusion occurring? And here we do actually see potentially interesting dependence on atmospheric river direction of travel with eastward traveling events, the dry intrusion reaching deeper into on average, deeper into the troposphere. You can see here, there's also some dependence on the atmospheric river intensity, possibly. So definitely interesting to investigate further. So kind of taking this even further, I estimate within the bounds capable by the MER2 data, an estimate for the ozone flux. So now this is basically integrating vertically the total amount of ozone in the dry intrusion. And again, this is divided by atmospheric river intensity and direction of travel. So consistent with the previous plots, orange is high intensity atmospheric river events, blue, low intensity atmospheric river events. On the left-hand side, I'm just showing sort of that composite maximum flux that is indicated on the left-hand side. So this is kilograms per meter squared per day. But on the right-hand side, I've integrated over the total about 2,000 by 2,000 kilometer area covering the atmospheric river and the ozone anomaly, and computing the mean composite flux of ozone in teragrams per day. Now, this is just all of December events. So that's why I'm sort of putting this unit of teragrams per day rather than trying to compute a full annual or like extrapolate an annual flux from just the December events. But that is definitely where I would go with this in the future. The total amount of ozone flux is very commensurate with what we see in connection with extratropical cyclones. So in this comparison, this is the December, January, February composite from the paper that I already referenced earlier that does a global climatology in connection with ECs. But there's also plenty of literature studies on individual events. And so this is a very significant amount of ozone flux into the troposphere. Some open questions related to this are: to what extent does the change in tropospheric ozone due to STT from atmospheric rivers and extratropical cyclones, et cetera, affect the global radiation budget? How will this trend continue as the climate warms further, given increases in frequency and intensity of atmospheric rivers? We see hints about this from various climate models. This is just one example, projection simulations of how we expect atmospheric river frequency and strength to change over time. So as I mentioned, I did actually do this in a three-dimensional sense, but I didn't quite have enough time to show you all of the wealth of data on this study. So here is the concentrations at 200, 300, 400 HPA. You've already seen the bottom two plots here. A huge thank you to my funding source, the Schmidt Science Fellows. This work wouldn't be possible without them. And of course, thank you to all of my collaborators at the Center for Astrophysics.
Great, thanks so much. We don't have time for questions right now, but we will have a discussion section at the end, or a discussion period at the end. Let me just mention that we are taking questions online for anyone participating online. So if you have questions, well, I'll pass it on to Christine here.
Yeah, so just go into the schedule and go to the session, and then there's a little blue button that says ask a question. So if you're online, please ask your questions that way, and we'll do the. And if you're in person, come up to the mic. So our next speaker is Chris Skinner, and he's going to be talking to us about the sensitivity of atmospheric rivers to climate forcing and their role in shaping regional climate change since the last glacial maximum. And Chris is one of our invited speakers. Take it away, Chris.
Am I using this? Hi, everyone. Hope you're doing well. I want to thank the conveners for inviting me to discuss some of the work that I've been doing with Juan Lora to understand the response of atmospheric rivers to various climate system forcings and the impact on hydroclimate since the last glacial maximum, which is about 20,000 years ago. And I want to acknowledge collaborators Jung Zhu and Clay Tabor, and funding from the NSF P2C2 program. So the broad motivation for this work is that we want to know whether or not atmospheric rivers have always had such a large role in Earth's climate throughout its history. And we want to know how and why that influence, that impact may have changed over time. If we can answer those questions, then we can better understand and interpret the climate signals that are recorded in paleoclimate proxies. And we can hopefully use those same proxies to increase our confidence in our understanding of atmospheric river responses to climate system forcings that are derived from the climate models. So we've run a set of climate simulations with different versions of the community or system model, and we've archived some high frequency output from these paleoclimate simulations to understand AR responses in different climate states in Earth's past, but also to individual climate system forcings that the Earth has experienced. So I'm going to share some results from two of those simulations. The first is from the last glacial maximum, which is a period characterized by relatively low CO2 and widespread ice sheets at the high latitudes. And then the early to mid-Holocene time period, which is characterized by enhanced seasonality, which means greater insolation in the boreal summer and less insolation in the boreal winter. We are using an AR algorithm that Juan put forth in 2017. That's been used for various paleoclimate studies at this point. So first, the LGM. So at the LGM, there were ice sheets that covered, large areas of northern North America, Europe, parts of the Patagonian Andes. And the presence of these ice sheets can influence ARs in multiple ways. You could think they could sort of divert the storm tracks and influence stationary wave patterns, but they can also act as a physical barrier upon which ARs can sort of make landfall and impact. And that process has been observed in the modern day in Antarctica and Greenland. So atmospheric rivers that make landfall on these ice sheets have really profound influences on precipitation. So they can lead to accumulation in the winter seasons. But in the summer, they can be quite warm, drop a lot of rain, and cause a lot of surface melt and actually some instabilities in the ice shelves. So if we look at the last glacial maximum, in the bottom right is the difference in AR frequency between the LGM and sort of the modern day or pre-industrial simulation. The big takeaway there is where you see all that brown, that's a reduction in AR frequency at the LGM. So ARs were considerably less frequent than they are today. And we've sort of attributed that to colder temperatures, lower ocean evaporation, lower water vapor in the atmosphere. There's some regions with increases, which are pretty interesting, but I'm not going to talk about those today. So there's this big reduction in AR frequency at the LGM. But if you look at the top where ARs are actually occurring during the LGM, you'll notice that ARs do make impact along the margins of the ice sheets. And in fact, across all of the terrestrial regions, the frequency of ARs along the ice sheet margins is higher than anywhere else on the planet. So we're interested in what the impact was on precipitation and hydroclimate in these regions. So the top plot is the percentage of all annual precipitation that was derived from atmospheric rivers. And on the bottom, we've sort of concentrated just on the ice sheet regions that are highlighted in orange there. So the box plots are consisting of different grid cells that are a part of the ice sheets. And we've sort of masked out the ocean there. So they're just the ice sheet grid cells. So if you look at the bottom left, it's the percent of precip from ARs again. And if you focus on, for example, the Cordilleran ice sheet in Western North America, the median value is about 10% of your precip from ARs, but it can be as high as like 22%. And then in the Laurentide ice sheet, the median value is like 18%, but it can be as high as 52% of the precip. So a pretty substantial role. And we've further broken this down into what percentage of your total rain and percentage of total snow do ARs contribute? And that's shown on the right. So rain is in blue and gray is in snow for the same regions. And you'll see that ARs are important for both of those, but they're relatively more important in supplying the rainfall to these ice sheet locations. So in the Laurentide ice sheet, for example, about 25% of all the rain that occurs came from atmospheric rivers, the median value, but it can be as high as 70% of all the rain. So a pretty substantial impact. And the reason for that deposit of rain onto the ice sheets is because temperatures during atmospheric rivers over ice sheets are generally warmer than average. And so the top is the average temperature during atmospheric river events for the winter season on the left and the summer season on the right. And so you can see that over the ice sheets, the colors are all blue there. That means temperatures are below zero on AR days at the surface on the ice sheets. And that's why in the winter you see snowfall and accumulation of snow on top of the ice sheets. But in summer, temperatures pretty substantially exceed the freezing mark, not just at the margins, but even extending a bit inwards towards the ice sheets. And then on the bottom, we're showing the temperature anomaly. So relative to the winter, what does a winter AR look like? And what is relative to the summer, what does a summer AR look like in terms of temperature? And you see that they are generally quite a bit warmer. So we wanted to understand what this meant for the surface mass balance of the ice sheets. And we used a fairly simple offline positive degree day scheme where if it's temperatures above freezing, that can lead to some melt, and we use some coefficient for determining that. We compared that with how much snow the ARs deposit on the ice sheets. And what we find in most locations is that ARs are actually removing mass from the ice sheets, or they should be. So they're actually causing surface melt. So they're sort of wasting away the ice sheets at the LGM. So to summarize this LGM work, AR frequencies are highest along the margins anywhere else in the terrestrial regions of the globe. And that can result in some pretty substantial amounts of precipitation. So about 50% of all precip in some locations came from ARs. But that precip is generally in the form of rain, and that can lead to surface melt conditions. And so when you have surface melt at the surface of a glacier or an ice sheet, that water can pool and then move down to the bottom of the ice sheet and lubricate the bottom. And that's been shown to sort of accelerate the demise of ice sheets. And so we actually are suggesting that this may have played a pretty big role in the retreat of the ice sheets at the end of the LGM, moving towards the warmer climate since then. So quickly, I want to touch on early mid-Holocene. So we've published this before. What we found is that ARs are incredibly sensitive to the amount of insolation during the year. And they're actually more sensitive to the summer insolation, but I'm showing the wintertime insolation here. So the middle plot there is the total change in precipitation between a mid-Holocene simulation and the modern day. And I'm highlighting the Western North American region, where it was considerably drier in the mid-Holocene. There's abundant proxy evidence for this. And what's shown on the right is the change in precipitation just to ARs between those two time periods. And what you notice is that the majority of the precipitation change in the total is actually just driven by the AR precipitation change. So ARs, we are identifying them as the mechanism for this drying in the mid-Holocene in Western North America. Importantly, you can also use proxies to hopefully sort of increase our confidence of what the models are saying. And so the example I'm giving here comes from a lacustrine core, so a small lake in the Southern Andes. And that bottom left plot's a lot going on in there, but this is from a paper by Lamy et al. In 2010. But what I want to highlight are those thick orange bars, and those are dated to the early and mid-Holocene, and they're indicative of really large terrestrial mass flows, so erosion and due to heavy precipitation that flowed down into the pond. And so they've been suggested to be indicators of extreme precipitation events in the early mid-Holocene, and then they've sort of stopped in the present day. And that's exactly what our model simulations are showing. ARs and extreme precipitation associated with ARs early mid-Holocene, and they have essentially stopped occurring at this location or much less frequent today. So that sort of gives us some confidence that the model is sort of giving us something that we actually saw in the real world. And I'm sure there are other proxy examples out there, and I'm curious to hear if anyone has any thoughts on what we could use. Lastly, I just want to mention the Paleo ArtMIP simulations. So AR detection is quite reliant on the algorithm that's used, and the same thing would be true of detecting Paleo ARs. And so we are making all of the simulations that we've conducted available to the Paleo ArtMIP project. And a few of these simulations have already run through all the different algorithms. And Juan created this nice multi-model mean plot there on the right of the influence of insolation on ARs and the influence of lower CO2 on ARs. And we have some other simulations that we're going to deposit into that repository. And then if you're curious about ARs and the robustness in paleoclimates, then be on the lookout for those coming soon. And I'll end there. Thanks.
We have time for a quick question. We have actually one online, but if you have one in person, you can come up to the mic. I'll start with the one that we have here. How do you detect ARs in the LGM simulation? Do you use a threshold metric that is the same as in the current climate?
Yeah, it's a good question. We are using, it's Juan's algorithm, which is pretty great, but it does have, it sort of combines threshold and percentile-based components. But it does use a IVT threshold that is derived from the modern day. So we are interested in looking at ARs that resemble the ARs that we see today for the most part. So if we did really relax that threshold, then we might see more ARs at the LGM because it is drier.
Okay, is that it? All right, I guess we'll move on to our next speaker. Okay, our next speaker is Hun Beck. And he will be talking to us about atmospheric river variability over the last millennium driven by annular modes.
Okay, so my talk is titled Atmospheric River Variability over the last millennium driven by annular modes. So a couple of talks before mine have already highlighted the importance of ARs, both from a dynamical perspective and a impacts perspective. I'd just like to reiterate that it's important to understand how ARs vary naturally. In particular, given that ARs operate primarily in the exotropics, understanding how ARs respond to exotropical climate variability is crucial, but this remains poorly understood. So this will be the motivation for my talk. In particular, the global role of annular modes of extratropical climate variability on ARs has not yet been investigated. So the annular modes are the dominant modes of extratropical atmosphere variability. They are the leading modes over the extratropics, accounting for about 30% of variance, either in the pressure field or the wind field. And they're called annular modes because they're zonally symmetric in structure. So here on the right, I show the southern, there's a figure showing the southern annular mode, and you can see that there is indeed a ring-like structure in the southern hemisphere. There's also a northern annular mode, which also shows a similarly annular structure, although it's a little bit less annular because of topography. For this presentation, I'll rely heavily on the CESM1 Last Millennium Ensemble, or the LME. The LME provides 12 members on daily resolution over 850 to 2005 AD. I note that this is over 5 million days of AR and annular mode sampling. Each member has identical radiative forcings, but a different realization of natural variability. So in sum, the LMA is a pretty powerful tool because it provides robust AR and annular mode sampling across the full range of radiative forcings that humans have experienced over the past 1,000 years. So how do we identify ARs? There's been many different AR algorithms. Here on the left, I highlight some that have been used. But for our talk today, we'll use an AR detection method that relies on daily integrated vapor transport. So this IVT formula right here. And in particular, we require, this is actually the same formula that the previous talk presented, but we require an IVT minimum threshold of 225 kilograms per meters per second. But then this term actually will scale with background integrated water vapor. So it does scale with changing climates. But when we apply this algorithm to the CESM1 model, in particular the CESM pre-industrial control model, and the MERIT-2 reanalysis data set, you see that we get similar climatological AR features. And this gives us confidence that the CESM model is realistically simulating ARs. Finally, because this is an annular mode study, I'm going to just briefly talk about how we calculate the annular modes. So we detrend daily zonal mean zonal winds, and we accomplish this by removing 10-year running averages. And then we remove the seasonal cycle from this detrended data and then perform EOF analyses on the resultant wind field anomalies. So the leading EOF over 20 to 70 degrees north will be the northern annular mode. And then likewise, the leading EOF over 20 to 70 south will be the southern annular mode. And then from now on, I'll refer to the northern annular mode as NAM, and then the southern annular mode as SAM. Okay, so that was our methods. So with that out of the way, let's get to our results. How do annular modes modulate AR activity over the last millennium? So here I'm showing regressions, positive composite and negative composites of AR activity onto the annular modes. The top row is showing NAM influences, and then the bottom row is showing SAM influences. The arrows are AR-driven IVT, and then the colors show AR-driven precipitation. I note that the direction of the positive composite, the positive phase of the annular modes are defined such that it's associated with the poleward displacement of the jets. So what we're seeing here is that during positive phases of the annular modes, we see an intensive, we see a strengthening of ARs over the subpolar latitudes and a weakening of ARs over the subtropical latitudes. And we see this both in the northern hemisphere, you can see it here, and then also in the southern hemisphere. And this is consistent with expectations because it is associated with polar displacements in the jets. For negative phases, we see largely opposite influences. So you see that what we see in the positive composite is largely reversed in the negative composite. Last thing to note here is that NAM's influence is most obvious in the northern hemisphere, but it does extend into the southern hemisphere. You can see that. Whereas SAM's influence is largely limited to the southern hemisphere. Here are regressions of AR-IVT onto the annular modes for the LME on the top row, and then the ARO5 data set on the bottom. This is just to show that the LME agrees very well with the reanalysis data set. So it gives us confidence that the CESM model and the LME in particular is well simulating the influence of the annular modes onto ARs. We perform EOF analysis onto AR frequency over 850 to 2005 AD, both in the Northern Hemisphere and the Southern Hemisphere. And we do this for all members. And the thing to note here is that this EOF analysis highlights the very same AR structure or similar AR structure that I showed before. So there's a dipole structure in the Northern Hemisphere and then a very annular structure in the Southern Hemisphere. And this indicates that the annular modes represent the primary means by which ARs have varied over the last 1,000 years. And here are normalized amplitudes of the principal components associated with the EOF1. And you can see that they are very steady across all 12 members, indicating that this EOF1 is robust across all 12 members. On the right are shown the composites that I showed before, but now on the left, I'm showing changes in mean AR activity. On the top is the change in mean activity from over the historical interval relative to the pre-industrial interval. And then on the bottom is the future RCP 8.5 AR activity relative to the historical interval. So there's not much change over the historical interval because of counterbalancing influences from aerosols and greenhouse gases. But over the future interval, we see very robust AR intensification on the order of about 20 millimeters per month in AR-driven precipitation. I note that this 20 millimeters per month is very significant because these changes caused by the largest, most prominent changes to AR activity are something like 20 to 25 millimeters per month. So our LME analyses provide a robust paleoclimate baseline from which to contextualize future AR change, and that they're actually rivaling each other. And lastly, we highlight the role of the annular modes onto integrated vapor transport more generally, of which ARs are a subset. Shown are regressions of IVT onto the annular modes, and then wind at 200 hectopascal onto the annular modes. And you can see that there's very big similarity between the two. And this just highlights the fact that the role of the annular modes onto the winds are largely affecting IVT and ARs. So I'm just going to leave these conclusions up here, but I have a minute, so I will take questions.
Plenty of time for questions.
Coming up to the mic, yeah, coming up.
Hello, very interesting talk. I have a question about applying those two paleo data. I was wondering if you have compared with some paleo proxy to see if like the AR activity is correlated with some proxy precipitation or things like that.
So this was a pure model study. In the future, I think there are data assimilation products that I could look that include the influence of tree rings, for instance, with the CESM LME. But for this study, this is purely a model study, and we compared to reanalysis data sets and other future and historical CESM experiments, but we did not look at paleoproxies for this study.
This is very interesting. I was curious if, so I know that EOF2 of the zonal wind is also thought to kind of play a role in the southern angular mode. I wonder if you'd considered looking at kind of the role of EOF2 for atmospheric rivers as well.
Yes, we looked at EOF 1, 2, 3. EOF 1 was clearly the annular mode structure. EOF 3 also looked kind of annular in annular. I'm embarrassed to say that I don't remember what EOF2 looks like.
Sorry, it's like a jet pulsing mode of variability. So it doesn't quite look annular in structure, but it's related.
Okay, so actually, I think we looked at EOF2. I think is often associated with the EKE structure, like the intensification and de-intensification of the EKE structure, I think. But I'm going to have to go back to that, actually. Yeah.
Thank you.
Thanks, Okay, our next speaker is Simon Lee. And Simon will be talking to us about modulation of atmospheric rivers by the Arctic stratospheric polar vortex.
Okay, thank you, and good morning to everyone who made it through the full week of AGU. So I'm Simon Lee. I'm a postdoc at Columbia working with Lorenzo Polvani, and this is some work which we put out a couple of months ago now, looking at how variability in the Arctic stratospheric polar vortex during winter is linked to variability in atmospheric rivers and their impacts. So I wanted to start by motivating the use of the stratospheric polar vortex in subseasonal to seasonal predictability. And I think the key thing to underline is that during winter, the Arctic stratosphere is the most predictable part of the extratropical atmosphere. Looking here at the northern annular mode, and thanks to the previous talk, I hopefully don't have to motivate the importance of that. The time scale, the E-folding time scale of the NAM in the lower stratosphere during winter exceeds 4 weeks. So this has a lot of potential predictability. And this variability in the NAM in the stratosphere has a robust downward impact on the tropospheric circulation, which primarily manifests in the North Atlantic sector, not so much in the Pacific sector, via modulating the North Atlantic oscillation and the latitude of the eddy-driven jet and the eddy-driven jet regimes. And so actually, subseasonal to seasonal prediction systems can capture this predictability. This figure here shows the day at which S2S models have mean squared skill score at which the models are skillful. And during midwinter, this goes out to at least the same time as the timescale of the NAM in terms of extratropical geopotential height. So this is something that models can represent. And models have shown better skill when initialized in particularly weak and strong vortex states. And there is seasonal skill in the NAO, which has been attributed to sudden stratospheric warmings and stratospheric variability. So all this variability in the stratosphere has been attributed to things like cold air outbreaks and their frequency and intensity, and also hydrometeorological variability, droughts and floods and extremes. And so it seemed natural for us to then ask, well, how does this variability in the vortex influence atmospheric rivers? So to do this, we've taken MERA-2 reanalysis. We did cross-check this with ERA interim, very similar results, so I won't show that here. And we're looking at DJFM when vortex variability and stratosphere-troposphere coupling is maximized. We used the Guan and Walliser AR catalog, but we did also cross-check the results with the Mundhenk catalog and get similar results. And so to diagnose our vortex strength, we're considering the anomaly of the daily mean zonal winds at 100 hectopascals and 60 north in the lower stratosphere where the time scale is the longest, where these are the most persistent. And we split them into terciles and consider the outer two as weak and strong vortex states, which gives us this daily classification of the anomalies through each winter. And hopefully you can see there that the blobs of blue and red are very large and long, indicating the persistence of these vortex states. And so in order to assess robustness of our results, we do a block bootstrapping procedure. So here we're looking at the frequency of atmospheric rivers during different vortex states. And when you look at the panels B and E, we're looking at when the vortex is weak. And what you can see compared with panel A is that there's an equatorward shift in the Atlantic, very pronounced, with an increased frequency of rivers in the Mediterranean and Iberia and decreased over Northwest Europe. There's also a very slight reduction in regions like British Columbia, but as expected from stratosphere-troposphere coupling, no huge change in the Pacific. When the vortex is strong, there's a significant poleward shift in the Atlantic and also an eastward extension into Scandinavia, bringing very large anomalies for Northwest Europe. And also this means that the highest frequency of atmospheric rivers over land anywhere during either vortex state or climatology is over places like Britain and Ireland during the strong vortex. So that's associated with the significant flooding events that we've seen during strong vortex winters in this part of the world. And there's also a slight increase in regions in the Pacific Northwest. So this is consistent with what we expect from shifts to the jet regimes in the Atlantic and NAO and AO phase modulation. It's important to note the perturbations are approximately equal and opposite, and that has a significant impact on what the outcome is based on the climatology in the two regions. And I think I should emphasize that these largest anomalies are, if you look at panels E and F, they are mainly over land. These anomalies are not maximized over the ocean, but over land where people live and where the impacts are. And so we can characterize this in terms of looking at atmospheric river landfall proportion or probability during each vortex state. And so that's what's shown here. And you can see that if places like the British Isles and Scandinavia, almost 50% of the landfalls of atmospheric rivers occur when the vortex is strong versus a minimal quantity when the vortex is weak. And then you get something approximately opposite for somewhere like Iberia at the other end of the North Atlantic. The maximum difference is for somewhere like Scandinavia, where you have the combination of the zonal, the latitudinal shift of the jet and an increase in its extent, its eastward extent. So a particular sensitivity there. And we also see smaller differences to places like Greenland and this small but significant change for places like Northern California and British Columbia. So still some Pacific signal. So we want to ask, how does this come about? Is this coming about due to changes to where atmospheric rivers form or just where they track and decay? And so what we're showing here is the probability of atmospheric river genesis and termination during each vortex state and its difference. And so what we see is that there's very little change to the probability of atmospheric river genesis depending on the vortex state, perhaps mostly confined to regions in the Mediterranean. But the main difference is coming from where the atmospheric rivers track. And so we see these large differences to the decay probabilities especially over Europe, but also over the Pacific Northwest and into British Columbia. And actually that leads to these two, what I like to call graveyards of atmospheric rivers, which are really pronounced during the strong vortex state, which is potentially associated with the most significant impacts from landfalling and terminating rivers. So then we wanted to think about how important is this for the actual impacts from rivers, the precipitation variability. And so we consider the seasonal scale now, and we're thinking of Europe, where the correlation between vortex strength on the seasonal scale and atmospheric river and precipitation is maximized. And so we're going to look at the DJFM total precipitation and the total AR frequency over Europe. And we're going to think about how does the precipitation variability, which is associated with the vortex variability, how is it modulated by this vortex modulation of atmospheric rivers? And so let's go through this piece by piece. First, we look at the regression of U100, this vortex strength metric on the seasonal scale with the river frequency, just frequency here. And we see this dipolar pattern as we saw with the composites earlier. Then we do the regression of the AR frequency with total precipitation, and we get this classic pattern highlighting the orography. Then we do the regression of U100 with total precipitation. So this is the pattern of precipitation variability associated with the vortex variability. And then if we multiply A and B together, we get the contribution to the precipitation variability that's modulated by both the vortex and the vortex modulation of the rivers, if that makes sense. And so what hopefully you can see is that C and D are rather similar. And in fact, where the most important impacts are, where the signal is highest, especially over places like Northwest Europe and Western Iberia and Eastern Mediterranean, this captures almost all of the signal, which means that atmospheric rivers are playing a key role in bringing about the precipitation response to anomalous stratospheric vortex states. And so to wrap this up, we find large differences to river frequency and landfall depending on the state of the vortex, and that's primarily in the Atlantic sector, but there are significant differences in the Pacific. These differences are largely arising due to changes in the atmospheric river tracks, not where they are forming. Most of the wintertime variability in total precipitation over Europe is arising due to the stratospheric modulation of atmospheric rivers. And that means that atmospheric rivers play a key role in bringing about the precipitation response to anomalous vortex states. And so I think future work, please do talk to me about this if you have any ideas, but I think it would be interesting to look if whether this is particularly associated with windows of opportunity for successful AR prediction. Thank you.
We have time for a quick question. If anyone in the room has a question, you can come up to the mic. You can also type in the chat or the ask a question bar from the schedule. There is an online question, so I'll just go ahead and ask you, Simon. Do you find a decrease in Siberian ARs, essentially all meridional dominant ARs?
Well, that's a good question. So if I just flip this back quickly, I don't think there is, it's possible that when the vortex is strong, that we're seeing slightly more going slightly further eastward into Siberia. So I expect that that's when we might see that, but I haven't looked at that explicitly, but that's a good question. Thank you.
Great, thank you very much.
Right.
Okay, so on to our next speaker, Annelies Swaling. Here we are. Annelies will be talking to us about using variable resolution grids to model atmospheric rivers around the Greenland ice sheet.
Alrighty. Hi, everyone. My name is Annelies Swaling. I am a graduate student from the University of New Hampshire. And like Christine said, I use variable resolution grids to model atmospheric rivers around Greenland. Like Chris Skinner was talking about, we care about atmospheric rivers in regard to glacial regions and Greenland specifically, because every so often a particularly impactful one will make its way to Greenland and cause a very short duration, high volume melt event. One such event occurred in July of 2012, where an atmospheric river made landfall with Greenland on July 8th and caused melt over nearly 97% of the ice sheet. And the mass loss from this event was above 3 standard deviations of the usual seasonal melt during this time. I use variable resolution grids to model my atmospheric rivers because the idea behind it is that we'll be able to have a better view of the atmosphere in that area in the same way that you would want to model topography with the highest resolution possible in order to pick up on all of the peaks and valleys that you're seeing. We're hoping that we'll be able to get a better view of the atmosphere using these variable resolution grids. You can see my 2 variable resolution grids, which I am using on the left and the right. On the left here, I have the Arctic grid, and on the right, I have Arctic GRIS. Both of these grids have a spacing of 111 kilometers on this outside region, and then moving into the Arctic, we zoom into 28 kilometers, and then further with Arctic GRIS, we zoom in to 14 kilometers. Variable resolution grids have been previously used in the Arctic to model surface mass balance with high fidelity. These 2 variable resolution grids here, VRC SM55 and 28, as compared to RACMO, the 28 kilometer view represented the surface mass balance the most accurately. They've also been used to model atmospheric rivers around the world, such as the Western United States. So my study is sort of in the interplay between those, looking at specifically Greenland and how well variable resolution grids model atmospheric rivers. There are a few questions which I am exploring. One is, how does the meteorology associated with atmospheric rivers vary based on grid type? And then how does melt vary based on different grid type? These 2 smaller questions are trying to inform the larger question of, do variable resolution grids actually resolve atmospheric rivers more accurately than other grid configurations? In addition to this, I am interested in how does melt vary regionally during landfalling atmospheric rivers. And this is informing the question of, how is melt actually affecting people who are living in Greenland? You can see in the green dots are places that people live in Greenland. So if more atmospheric rivers are making landfall on this western edge, that will be more impactful to people living there. And I'm focusing on these 2 questions circled in red for the talk today. So the 3 different grid configurations which I am looking at are all run from 1979 to 1998. They are free evolving and they are in an AMIP style configuration. On the left, you can see my 2 finite volume grids. They are standard lat long grids. They have spacing of 278 kilometers and 139. In the middle, I have my 2 spectral element grids. They are unstructured and they have a grid spacing of 167 and 111 kilometers. And then my variable resolution grids, like we saw earlier, 111 on the outside, zooming into 28 kilometers, and then further into 14 kilometers. So the first step in my research is remapping all of my grids to F19 and NE30 PG2 grids. This is so that we can compare them to each other accurately. I remapped using ESMF and Tempest Remap. So with remapping all of my grids to these two things with two different methods, we ended up with 4 different ensemble components. After we remapped, we used 2 algorithms within the Tempest Extremes package, Detect Blobs and Stitch Blobs. Detect Blobs spits out your data as a binary mask, and it basically looks for the whole global view where are atmospheric rivers, and you can see them here. And then Stitch Blobs goes in looking at that binary mask and is able to pick apart the discrete atmospheric rivers. And we need it to pick apart the individual atmospheric rivers and ID them because after that, we saw which atmospheric rivers were actually intersecting with Greenland. After finding those which were intersecting with Greenland, we were able to create a composite mask, which sort of showed the whole union of the storm track as an atmospheric river was moving across the ice sheet. This is not how they actually move across. This was just for the sake of a nice figure here. But you see that my composite mask would be this area in the purple hatch. And then after we have that mask, we are able to look at the meteorology from CLM and CAM to see how it is changing during that time the atmospheric river was moving over the ice sheet in this specific region. So looking here, we have a specific, the Arctic GRIS mapped to F19 with Tempest Remap. This is one of the 24 plots of this kind. You can see that 520 atmospheric rivers intersected with Greenland from this grid configuration. We took each of those individual intersecting atmospheric rivers, found the point at which it was maximally overlapping the ice sheet, and took that as time t. This allowed us to sort of stack all of those different events on top of each other, fulcrum pointed at that time t, and look backwards 3 days in time, forwards 3 days in time to see how, and then average all of those events together to see how precipitation was changing as the atmospheric river was making landfall. You can imagine that looking at 24 of those plots at a time is pretty unhelpful. So we made some line plots. Looking at the top here, we have integrated precipitation, so the sort of sum of all of the precip during those storms. And on the bottom, we have the precipitation rate. So in blue, we have the finite volume grids. In the orange-red colors, we have the spectral element. And in the greens, we have my variable resolution grids. And you're seeing that the variable resolution grids are actually producing the smallest amount of integrated precipitation. So that was a really interesting finding. And we think that it is due to the area which are actually covered by atmospheric rivers while they're landfalling. You can see that in these finite volume and spectral element, they have much more of the ice sheet which are covered by these purple areas, which the atmospheric rivers were touching as compared to the Arctic GRIS. And this sort of theory was supported by the average precipitation rates. You can see that here, all of the precipitation rates are pretty similar. So there's not so much difference happening in the rates themselves, but it is due to this area. We also looked at melt in the variable resolution grids, the same sort of color convention as before. And you see that the variable resolution grids are producing the highest amount of melt. So this was also a very interesting finding. We think that it is due to the higher gradient supported by the variable resolution grids. So whatever meteorological factor is forcing the melt, we are unsure yet. We think that it is due to those gradients. And another interesting thing that we are seeing is this lag occurring. There's still pretty significant melt happening up to 1 or maybe even 2 days after the event is over the maximum extent. So we see that atmospheric rivers are penetrating less far into the ice sheet in the variable resolution grids. We see that there is less precipitation due to that, the atmospheric rivers stopping further onto the western margin. And we see that there is less melt with the higher melt with the variable resolution grids as compared to the 2 other grid configurations. So we see how the grids compare to each other, and now the next step will be actually seeing which one is the more accurate. We plan to compare this data to ERA 5. And then finally, I'm interested in exploring how the mechanisms are actually forcing that increased melt in the variable resolution grids. So thank you all for listening, and that is my conclusion.
Does anyone have a question for me? Ali, come on up.
Nice job. Did you find that in your variable resolution grids, the atmospheric rivers themselves were finer with like tighter gradients?
Yes, indeed we did. Yeah, so they were having just higher IVT as well. Yeah. Thank you all.
All right. So thank you, Annalise. Our next presentation is from Renee Guerrero. And Renee will be talking to us about zonal atmospheric rivers impinging on the west coast of extratropical South America, a silent threat.
Thank you. Thank you, the conveners, for probably the most interesting session of this conference. I'm Renee Guerrero from University of Chile and the Center of Climate and Resilience Research. And I will talk to you about these zonal atmospheric rivers. Let me explain what is this. So, well, first of all, obviously, all you are big fans of atmospheric rivers. And if you want to continue your investigation, of course, visit Chile. In fact, some of you visit Chile for an IR conference that we have in October, because we have probably the most, one of the highest frequencies of landfalling ARs in the world. Several dozen of atmospheric rivers reach the southern Chile and the southern Andes every year. And here are two climatologists showing this. And of course, if each atmospheric river has its own flavor that's produced different impacts. You can classify strong and weak. Some people classify between windier and moisture. I would suggest that this classification between tilted and zonal atmospheric rivers is very interesting for us. So let me start with something which is not at zonal atmospheric rivers. In fact, when I grew up, this was the kind of storm that we were really concerned with, a very well-developed low pressure here, a cold front, a warm front, etc. And indeed, these tilted ARs, well, in fact, here, well, this is not IVT, but this is, you can see the precipitable water, very well tilted with a 45 degrees angle approximately with the Andes. And they produce significant amount of precipitation. And they, in general, they are favorable because, as I will show, they tend to be cold. They tend to produce most of the precipitation during the cold phase of the storm. So here, for instance, we got something between 50 to 100 millimeters per day, which is significant for central Chile, but with relatively cold condition with freezing level about between 2,000 to 1,500 meters above sea level. Remember that the Andes has around 500 kilometers in this region. So this range of elevation of the freezing level produce significant amount of snow over the mountains. Now, this is the same, excuse me, the same storm that I showed you before, but here I just brought the picture. So here I had this low. There is another low here about, I don't know, 3,000 kilometers to the west. And this is August 8th. A few days later, this moisture, which is actually seen here by the clouds, these MODIS satellite clouds, have reached the coast of central and southern Chile. But now look that there is no really a very strong signature in terms of something like a low, but it's rather a very zonal stream of clouds and moisture reaching central Chile and southern Chile. And look how different is now how the moisture is approaching central Chile. Here is relatively almost completely zonal. There is no much synoptic forcing in this case, because if you look, these are the winds, I believe that are, 500, well, let's say 150, but it could be 500. So there is not a big trough producing large scale accent in terms of quasi-geostrophic accent. But of course, with this stream of moist air impinging the Andes, most of this air has to be lifted and produce precipitation here in central Chile. So this is a zonal AR. And this is also produced significant precipitation, again, between 50 and 100 millimeters over central Chile. But that's happened with relatively warm conditions in which the freezing level was around 3,000, over 3,000 meters above sea level. So it's much higher than the previous storm. And in fact, this is a zoom of this is the condition in the Andes here before this storm. And you can see now how the storm actually produced a reduction of the snow cover, which means that we have rain over snow, and part of this rain was able to melt the snow that was previously on ground. So again, in addition to the precipitation, you could have an additional source of water because of this melting. This is a more recent case study. Again, you can see here this 3,000 or 4,000 kilometers long zonal atmospheric river. This is the infrared images showing how this all this moisture is coming to central Chile and producing precipitation. In this case, that was just a few months ago. Well, we did radiosounds and we did much more observations. Notice how saturated is the atmosphere in this case. And you see the zonal flow here, except here below the, let's say, 700 hectopascal, where the mountains, both the Andes and the coastal range, block the flow and produce this northerly flow. But over this area, over this layer, you have this completely zonal flow. Remember that the crest of the Andes is about 500 hectopascal. So there is still a lot of winds going directly toward the Andes and producing precipitation. And now we have this MRR, which is a micro rain radar looking upward. So this is the 24 hours of this storm, and I focus in this particular in this panel, which is the vertical velocity of the hydrometeors. So you clearly can see the distinction here between the snow and the rain. So in this case, I will argue that we have within the storm, we have this ROS, this rain over snow, because here the freezing level, and in fact, these are the radiosonde data, was about, again, 1,000 meters. And during the storm, it reached 2,000 meters. So it was quite significant. And again, that can have a significant hydrological impact. Just to reiterate this, not only precipitation matters in our case, because the Andes is so high, about 5,000 meters above sea level, any variation in the snow line or the freezing level produce quite significant response, hydrological response, at least in the area where the rain is receiving rain. And this is a complicated graph, but basically said, obviously the highest the freezing level, the most pluvial area you have, and that can have significant hydrological consequences. This is my last case. This happened, notice I put here this red line because that's happened between, at the end of January of 2021. January is our winter. Of course, we're in the southern hemisphere and it's bone dry in central Chile. Still, we have a very significant precipitation event with something about 100 millimeters. So this was a major storm, produced cuts in roads, a landslide, significant impact in agriculture and tourism, etc. So we did a case study. Here is a reference in case you want to see this. Of course, I am showing this because again, was a zonal atmospheric river. Here you have the precipitable water. Notice how zonal is this area. And I use in this case just to provide you a background of what were the previous condition. So the storm occurred here around the 29. So here you have the colors is the precipitable water and the contours, I believe, is 500 hectopascal geopotential height. So again, this is the day of the storm. But if you look backward, 26, for instance, 26th of January, this is the configuration, and this is something that we see recurrently in these cases. You have a cyclone in the subtropics. You have a ridge in the middle latitudes. And that's, we believe, is quite important in supporting these atmospheric rivers because you have this configuration. You have, actually, this can be a blocking high that's put or push cold air to the north. Here you have the low that's put warm air to the south and also moist air. So the low produce transport moist air. And together, these two streams of airs tighten the thermal gradient that enhance the jet. And I think that this is the combination that you need to have these zonal atmospheric rivers. You'd have to put a very strong zonal contrast in temperature. And then with the moisture provided by the low, this goes directly toward Chile. These are similar, but 500 hectopascal. And this is just a diagram, not showing that even though the storm was around the end of January, this configuration was present a week or even 2 weeks before. And that's opened a little bit the opportunity to look this not only in the synoptic context, but also in a few days in advance. So these are my take-home messages. Of course, ARs oriented in the zonal direction, maximize the water vapor that's accent over the mountains, over the Andes, start produce moderate to strong precipitation. They can remain, I didn't say that, but they can remain stationary for several days or 1 or 2 or even 3 days. And the precipitation occurs in this prefrontal sector, which maximize the rain over high elevations. And there is at least one recurrent large-scale circulation pattern that is in place several days before, and we're investigating this. We haven't done yet a climatological study, but we're advancing on this, and any comments will be much appreciated. Thank you very much again.
So I think we have a time for one quick question. I think we have one in the audience.
Hi, Renee, great talk. I just wanted to point out that this kind of pattern happens on the West Coast of North America as well. And the confluence between like a low parked over the North Pacific and a high pressure to the north makes the moisture enhancement. So it doesn't have to actually tap into a moisture source. It's just local convergence and confluence along that line. So it sounds very similar to the cases that you're showing here.
Good to hear that. Of course, the angle of the coastline here is different. So yeah, you tend to have more normal situations because, well, we can discuss this, but it's interesting that there is similarities and some differences as well.
Yeah.
Thank you, Lynn.
Yeah, great.
So just a reminder, thanks, Renee. We have a discussion question at the end. So we'll do your question and discussion so we can move on. So yes, our next talk is Wei Ming Ma. And Wei Ming will be talking to us about evaluating the representations of atmospheric rivers and associated precipitation in reanalysis with satellite observation.
Good morning, everyone. My name is Wei Ming Ma. I'm a recent graduate from UCLA. In this presentation, I'm going to talk about evaluating the representation of atmospheric rivers and their associated precipitations in reanalysis with satellite observations. Atmospheric rivers, or ARs, are long and narrow filaments of strong moisture transport in the atmospheres. As shown in these satellite loops, this feature can be easily identified in the fields of integrated water vapors. Previous AR study usually relies on the integrated water vapor transport, or IVTs, from the analysis to identify and characterize these events. However, the uncertainties in the representation of these events and their precipitations remain unknown. In the analysis, remain unknown. Satellite data provide direct observations on the characteristics of ARs. Previous satellite-based AR studies detect AR usually based only on the integrated water vapors or the IWV fields. And usually a simple threshold of 2 centimeters apply to the IWV fields to detect these ARs. However, detecting AR using only the moisture fields can sometimes detect those features with very strong moisture contents, but weak wind components, therefore weak transports. And furthermore, this kind of simple thresholds can only work for certain regions. That's why, to the best of my knowledge, of the previous satellite-based AR studies are usually regionals. So in this study, we are going to improve these limitations by developing AR detection algorithms for satellite observations using not only the moisture field, but also wind informations. We know that since the 3D wind field is not available in satellite observations, in the first step, we are going to derive the geostrophic winds from geopotential heights at 4 different pressure levels located in the lower tropospheres. We then vertically average the geostrophic winds and combine it with the IWV to derive what we call the geostrophic IVT. As shown in the upper right figures, it shows a snapshot of the IVT from ERA5 and also the corresponding GIVT from ERA5. You can see that the GIVT is nearly identical to the IVT. And indeed, we found that based on the SOI PDF of the IVT and GIVT from ERA5, we can see that nearly all pair of the IVT and GIVT fall along the one-to-one rise, suggesting that GIVT can serve as a good proxy for IVT. We then use this GIVT as an input to the modified Guan and Walliser 2015 algorithms to detect ARs. And I will talk more about this modified Guan and Walliser 2015 algorithm in the next slides. And for observations, we use the daily IWV and geopotential heights from the air AMSU. And daily precipitation is based on the IMERS datasets. And 7 commonly used reanalyses are also imported in these studies. The Guan and Walliser 2015 algorithm is a widely used algorithm in the AR communities. And notable criterion employed in this algorithm include a threshold, which is the 85th percentile of the IVT magnitudes. And also 3 criterions related to the IVT directions and 2 criterions related to the geometries of the detected AR. And using the original algorithms, we found that the AR frequencies based on GIVTs is lower over the mid-latitude compared to the AR frequency based on the IVTs, but higher over the subtropical oceans. And then after some sensitivity testings, we found that once we remove the 3 criterion related to the IVT directions, the AR frequency based on GIVT is nearly identical to the AR frequency based on IVT. So the algorithm used in these studies is the Gon and Walliser 2015 algorithm, but with the 3 criterion related to the IVT direction removed. So let's first look at the AR frequency distributions. And in this study, AR frequency is simply defined as the fraction of time a grid point experience AR conditions. Panel A is showing the AR frequencies in satellite observations. We can see that enhanced AR frequency can be found over the mid-latitude regions. And compared to satellite observations, lead analysis tend to simulate fewer AR over the subtropical oceans and slightly more AR over the high latitude regions. And over the mid-latitude regions, the AR frequencies in the analysis is quite consistent with that in the satellite observations. And also based on the zonal mean difference between the analysis and satellite observations, we found that the spread in the AR frequency across the analysis is small. The panel A here is showing the AR length distributions in different data sets. We found that the spread in the AR length distribution across different data sets is small, with AR in satellite observations slightly longer than the AR in the analysis. And however, for the AR width distribution, as shown in B, we found a relatively larger splash. AR in B2 tend to be narrower, and AR in the NCEP R1, NCEP R2, and CFSRs tend to be broader. And we also look at the A is showing the AR precipitation intensity in satellite observations.
Recording in progress.
Hi, my name is Ola Layospour. I'm a PhD student at University at Buffalo, and today I will present our work with my advisors, Dr. Kang Soon from University at Buffalo, and Dr. Caroline Nola and Dr. Gonzalo Gonzalez-Abad from Harvard-Smithsonian Center for Astrophysics. This work is to estimate emissions directly from satellite observations, and we would like to acknowledge NASA and MethaneSat for supporting this research. So short-lived air pollutants such as oxides of nitrogen and volatile organic compounds play important roles in tropospheric chemistry, and they lead to surface ozone and particulate matter pollution, but they cannot be directly measured from space. However, NO2 and formaldehyde are good proxies of NOx and VOCs, and they can be directly observed from space using different satellite instruments. And on the leading edge is TROPOMI, which provides daily global coverage of NO2 and formaldehyde column amounts with high spatial resolution. So after August 2019, the spatial resolution is 5.5 by 3.5 kilometers. And this study aims to calculate NOx and formaldehyde emissions directly from TROPOMI observation over the US. So satellite remote sensing data can be presented in different formats. For example, level 1 data are the calibrated georeferenced spectra derived from raw level 0 data, and level 2 data are the retrieved quantities from level 1 data, and level 3 data are the level 2 data mapped on a regular grid, and level 4 data is the model output from analysis of lower level data emission in this work. And so the goal goal is to derive emission level 4 from retrieved column amounts level 2 or 3. So satellite level 2 data are irregular due to viewing geometry and missing data. In this study, we used physical oversampling approach in order to oversample satellite pixels on a regular grid and produce level 3 data. It's an object-oriented, parallelized, and open source algorithm to average level 2 data to level 3. Here on the top left, you can see 1 day of tropomi level 2 data, and on the bottom left, you can see level 3 tropomi NO2 averaged over a month. And on the right panel, you can see the speed to run this algorithm. I would also like to mention that level 4 emissions are derived within the same framework in this study. So now let's see how we calculate emission. So in our method, in order to calculate emissions, there are 3 terms involved: a directional derivative term, wind topography term, and chemical loss term. So we derive this equation using the first principles and mass balance. So in this equation, E stands for emission, omega is column amount, U is wind vector, which we use ERA5 reanalysis data, X is the inverse scale height, and Z0 is surface altitude, tau is the chemical lifetime. X and tau are obtained through fitting, which I will explain in the next slide. But for now, I would like to compare our method with previous studies which were based on flux divergence method. So in order to do that, I've split the first right-hand side term of the above equation into 2 terms here, which using the product rule. So by looking at the bottom equation, the second and the third term were not considered in flux divergence studies, which may actually play important roles depending on the column amount and terrain roughness. So now we have the emission equation and we want to find inverse scale height and chemical lifetime. In order to do that, we selected the grid cells in which the emissions are very small relative to other terms, so the emission term can be neglected. And the equation can be transferred into it becomes a linear regression model. And then beta 1, which is an estimator of minus X, and beta 2, which is an estimator of minus 1 over tau, they are fitted to obtain inverse scale height and chemical lifetime. Fitting can be conducted each calendar month or climatological month, depending on the signal to noise ratio. Here you can see the scale heights for different molecules with different lifetimes. In addition to NO2 and formaldehyde, in this plot, I've also included CO and methane scale heights calculated with within the same methodology. So well-mixed species such as formaldehyde, which is shown by red.
Recording in progress.
Comparing that to ERA5, also at a 1 hourly temporal resolution, but that's a finer spatial resolution. So 1/4 degree instead of 1/2 degree. As well as JRA55, much more coarse, 6 hourly, 1.25 degrees. JRA55 was primarily included because we also wanted to know how well century scale reanalyses are producing the atmospheric rivers with these different detection tools. So we were able to compare JRA55 to JRA55C, which only assimilates conventional data. So I'm not really going to be discussing that today. Instead, we're going to look at how the uncertainty in AR frequency in the reanalyses compares to the uncertainty for the detection tool and how this impacts the diagnostic variables like precipitation. So first, we're going to start off by just kind of looking at the PDF of IVT in the 3 different reanalyses using the categorical scale developed by Marty Ralph from his 2019 BAMS paper. So we have category 1, which is a pretty much a weak atmospheric river, going to category 5, which would be detrimental if it were to make landfall. So on the top, I have the frequency for each of these categories in MERA 2. So you can see that category 1 is more broadly shaped in terms of the spatial pattern. And as you get to those higher intensities, you'll notice that the core of where the atmospheric rivers are occurring becomes more fine and more frequent. Comparing this to ERA 5, you'll notice right off the bat, there are more atmospheric rivers in MERA 2, and that's because climatologically, MERA 2 has a higher value for total precipitable water vapor, which translate into more IVT. This is especially the case for that category 5, and that's the same for JRA 55. So JRA 55, with it being so coarse, what's happening is it's not really able to capture those very, very intense atmospheric rivers, and instead it's going to get more of these weak to moderate ARs. So now we're going to look at all of the different detection tools that submitted to the reanalysis intercomparison. So we have 10 different ones here. There's a very big variety from deep learning, object identification, relative thresholds, absolute thresholds, but pretty much everyone agrees, as you can see in the ensemble mean, that there are 5 main AR cores around the globe, particularly over the ocean regions, but the standard deviation indicates that not everybody's really agreeing on the relative frequency of these ARs. There's a couple that I want to point out in particular here. That's the Guan-Walliser. This happens to be a very widely used algorithm, as we've seen in our previous talks. So the way that the Guan-Walliser algorithm works, it tends to eliminate that equator dipole gradient. And so you can see that it allows more atmospheric rivers over land. And that's going to be important when we're looking at precipitation. The other ones that I want to point out are these regional ones, IDL, Paine, and Will. And those are for very specific purposes. So when you're comparing to those global algorithms, you'll notice that in general, they don't quite capture as many atmospheric rivers. Comparing this to ERA 5, as we noticed before, we have in general more atmospheric rivers in MERA 2. This is not necessarily the case for algorithms like Guan-Walliser and Mundank, and that's because these are using those percentile-based thresholds. So if you're using a relative threshold, like we see in the case for READ 500, where you need at least 500 for your value of IVT, you're less likely to actually detect that atmospheric river. ClimateNet really stands out here. I don't really want to call that one out too much, but what my theory is that it's the deep learning method, and I don't think they really have a sufficient training data set, because that required manual experts labeling whether or not there was an atmospheric river. So perhaps with additional training data, it would look more comparable to MERA 2. The results for JRA 55 are actually quite similar. So we're going to be using the idea of a consensus atmospheric river, and that's when at least half of the ARDTs detect an AR at a grid box and time step. And so unsurprisingly, MERA 2 has the most atmospheric rivers. And when we do that as a percentage, we can really see that the ARDTs are agreeing on the core of the atmospheric river, but not really the periphery. What I really found more interesting was when the reanalyses agreed and disagreed with one another. Because there's more atmospheric rivers in MERA 2, you're more likely to agree with JRA 55 or ERA 5 than if you're looking at all 3 or ERA 5 compared to JRA 55. But the disagreement is interesting because that's when MERA 2 didn't detect an AR that was detected by ERA 5 or JRA 55. In the case of ERA 5, you see that around the northern periphery of the AR core, you're detecting more atmospheric rivers. You're also allowing more to penetrate into the Pacific Northwest. And that could be possible just due to that finer spatial resolution, that it's allowing the atmospheric rivers to go in between mountains in order to get into interior like Oregon. JRA 55, so you can see that it's the differences within the core, and it's almost indicative as though it could be related to temporal resolution. So perhaps with that 6 hourly being matched up to the 1 hourly, you're allowing an atmospheric river to travel faster or traveling slower in one reanalysis compared to the other. So in terms of precipitation, we really wanted to look at that because that's how we're really seeing the impacts. And I use an independent data source for this, the CPCU daily quarter-degree gridded observations. So we see that the spatial pattern of the air precipitation is dictated by topography, but the percentage is dictated by the frequency of the atmospheric river. We have more precipitation ERA 5, and that's because you're detecting less but more intense atmospheric rivers. So when you average that out, you see more precipitation per event. And so a lot of people can use this consensus AR type of methodology, or you can use an ensemble approach where you just average every single ARDT that's thrown into the mix. And when you compare these, you'll notice that the consensus atmospheric river is going to give you more precipitation right along the coastline, but the ensemble mean is going to see a bit. Oh no, I'm the opposite. So inland precipitation is less than the ensemble mean. But if you're including an algorithm like Guan-Walliser, that's going to allow it to penetrate and get the precipitation there for the ensemble mean, but it's going to be tossed to the side for the consensus. So in the interest of time, I'm just going to leave up my summary slide here, but I really want to highlight these last couple bullets. So please participate in ArtMIP. All of the data for the AR tags for the reanalysis, intercomparison, and the other tier 1 and tier 2 projects are available. We'd love to have you participate and put out some more studies. Thanks.
Ali, we got a quick question.
Sure.
Do the reanalyses disagree more on the yes or no of the existence of an AR, or more on the AR boundary line?
I think they agree more with the fact that there is an atmospheric river, but there is some discrepancy with the boundary line, and that's particularly the case because ERA 5 they're really finer with these more intense gradients from the core to the periphery, and so it is the boundary as well.
Thanks again, Ali, and great representation for ArtMIP.
Okay, thank you to all the speakers. Let's transition to the discussion. We have just a few minutes, but there are a huge number of questions online. And if anyone in the room has questions, please come up with the mic. We'll try to get through as many as we can and go from there.
So I wanted to call Kirsten back up because you didn't get to ask a question. So I wanted you to take the first online question while people think and come up to the mics if they want. Let me get this one. Kirsten, are there different processes related to the two bins on each side, i.e. different processes related to more zonal or more meridional directions?
So you're saying differences in reference to like direction of travel for the atmospheric rivers?
I'm not sure who wrote it. So,
yeah. Yeah, I would say that the sample is really quite uniform, but there one place where I would highlight differences is in the east traveling bin. So like that first bin, the overall intensities are a little bit different when you're trying to divide them by the 50th percentile compared to all